Morning. So myself, Dr. AMALRAJ, Assistant Professor, PG and Research Department of Chemistry, St.Joseph College of Arts and Science, Autonomous, Cuddalore. Today, we are going to discuss about the basic implication of IR spectroscopy or infrared spectroscopy. So before seeing the IR spectroscopy, we have to know about the introductions. Why IR spectroscopy are using in analytical technique? So it is an important analytic technique for determining the structures of both inorganic as well as organic compound. This spectroscopy, IS spectroscopy, are known as vibrational and rotational spectroscopy. It lies in the wavelength ranges of 0.8 to 200. This technique provides a spectrum containing a large number of absorption bands from which a wealth of informations can be derived about the structure of organic compound. When IR light is passed through a sample of an organic compound, some of the frequency are observed while other frequencies are transmitted through the sample without being observed. If you plot observance or transmittance against frequency, the result called as infrared spectrum. So application of IR spectroscopy. Identification of functional group and structural isolation of organic compound. Quantitative analysis of a number of organic compounds. Study of covalent bond in molecules. Studying the progress of reactions. Detection of impurities in a compound. Ratio of cis-trans isomers in a mixture of compounds. Shape of symmetry of an inorganic molecules. Study the presence of water in its samples. Measurement of paint and varnishes. So these are the application of IR spectroscopy. So limitation of IR spectroscopy. It cannot determine the molecular weight of the compound. It does not give information about the relative positions of different functional groups in a molecule. From the single IR spectrum of an unknown substance, it is not possible to know whether it is pure compound or a mixture of compound. From sample cells are made up of halogen salt, which are susceptible to moisture. Gas samples cannot be analyzed as they lack sensitivity. So these are the limitations of IR spectroscopy. So when a chemical sample is exposed to the IR light, it can observe specific frequency and allow the rest to pass through it. Some of the light can be reflected back to the source. Transmittance T is defined as the radiative power transferred by a sample to the radiative power incident on the samples, whereas observance A is equal to log of 10 1 by T. And as IR spectrum is usually plotted using transmittance, hence observing band appear as dip rather than maximum. Each dip is called band or peak. So most of the IR spectrums will run in transmissions. So classification of IR bands. Here there are three bands: there weak, medium, strong. So IR band classified as strong, medium, and weak. So depending on the relative intensity in the IR spectrum. A strong band covers most of the y-axis. See, a strong band covers most of the y-axis. A medium band falls about half of the y-axis, and a weak band falls to about 1/3 or less of the y-axis. So these are the three bands observed in IR spectroscopy. The principle of IR spectroscopy. When the energy, the form of IR is applied, and if the applied IR frequency is equal to the natural frequency of vibrations, the absorption of IR take place and a peak is observed. Molecules are excited to the higher energy state from ground state when they observe higher radiations. When a compound is exposed to higher radiations, it selectively absorbs the radiation, resulting in vibration of the molecule of the compound, giving rise to closely packed absorption band called as IR absorption spectrum. The band corresponds to the characteristic functional group and the bond present in the chemical substance. Thus, an IR spectrum of compound is considered as the fingerprint for its chemical identifications. Dipole moments. It is defined as the product of internuclear distance between bonded atom and the charge present in bonded atoms. See, the distance between the atom. It is a vector quantity. It measures the bond polarity. The formula dipole mu is equal to Q into L. So dipole moment is a measure in terms of electronegativity. That's why it is direction is always towards the most electronegative atom. See, A moves towards the B. So B is more electronegative than A. That's why B is partially negative charge, A is partially positive charge. Dipole moment and symmetry of molecules. The bond in a molecule can absorb higher radiations only when there is a change in dipole moment due to electric field of higher radiations. The electric charge positive and negative on the atom of the molecule experience forces in opposite directions. As a result, spacing between the charged atom of the molecule also decreases. These charged atoms, when vibrated, absorb higher radiations. If the rate of vibration in charged atom is fast, they exhibit intense absorption of radiations and vice versa. Vibration frequency of carbonyl, amine and alcohol group, etc. occurs to change in dipole moment, thus absorb higher radiations. Symmetrical diatomic molecules like oxygen, nitrogen, halogens do not possess electric dipole and hence cannot absorb higher radiations. So when it comes to types of molecular vibrations, so molecular vibrations are divided to two types. One is fundamental vibrations, another one is non-fundamental vibrations. Here we are going to discuss about the fundamental vibrations. The fundamental vibrations are divided into two types. One is called stretching vibrations and bending vibrations. The stretching vibrations divided into two types, symmetric, asymmetric. Whereas bending vibrations divided into two types, in-plane bending, out-plane bending. In in-plane bending vibrations, it divided into two types, scissoring or rockings. So out-of-plane bending is further divided into two types, bagging and twisting. So non-fundamental vibrations are divided into four types: overtone, combination tones, Fermi resonance, etc. So when it comes to molecular vibrations, molecules are made up of atoms linked by bond. The movement of atom and the chemical bond like spring and balls. So think the atom like a ball and ball like a spring. So when this molecule absorbs higher radiations, it is set into vibration, resulting in excitation of bond deformation, that is stretching and bending. First, stretching vibrations. They involve movement of atom within the same bond axis, such that the bond length change without any change in bond angle in a regular intervals. These we call as stretching vibrations. See here, the bond angle doesn't change, only the bond length getting changes. So we call this as stretching vibrations. It requires more energy, so appear at shorter wavelength or higher frequency, 4000 to 1250 centimeters. These stretching vibrations divided in two types: symmetrical stretching, asymmetric stretching. The atom of a molecule either move away or towards the central atom, but in the same directions we call as symmetrical stretching. See here from the central atoms, the atom approach the central atoms and depart from the central atoms. Both are atoms move in the same directions, either towards the central atom or away from the central atom. So we call this as a symmetrical stretching. When come to asymmetric stretching, so one atom approach the central atom while the other depart from it the central atoms. We call this stretching as an asymmetric stretching. Bending or deforming vibrations. So they involve movement of atoms which are attracted to a common central atoms, such that there is a change in bond axis and bond angle of each individual atom without change in their bond length. So bending deformations refers to the length of the bond length doesn't change, whereas the bond axis or bond angle getting changes. We call this as an bending vibrations or deforming vibrations. For these bending vibrations generally require less energy and occurs at longer wavelengths, approximately 1440 to 666 centimeter inverse. These bending vibrations are further divided into two types: in-plane bending vibrations, out-plane bending vibrations. In in-plane bending vibrations, we are going to see the two type of in-plane bending vibrations. One is called as rocking and is called as scissoring. When come to rocking, in plane bending of atom occurs wherein they swing back and forth with respect to the central atom. See here, the atom occurs, they swing front and back with respect to the central atoms. Here, the bond length getting doesn't changes, whereas the bond angle getting changes. Okay. The movement of atom take place in the same directions. Change in angle between a group of atoms. When it comes to scissoring, in plane bending of atoms occurs wherein they move back and forth. They approach to each other. So the bond angle and also the bond axis getting decreases. The bond length doesn't change. See here, the second bond angles are decreases. Outplane vibrations, further divided into two types: wagging, twisting. Two atoms oscillate up and below the plane with respect to the central atoms. We call as wagging. Twisting, one of the atom move up the plane while other down the plane with respect to the central atom. See here, one atom far, another atom near, far near. So we call this as twisting. Diagram for symmetric stretching, asymmetric stretching, scissoring, rocking, wagging, and twisting. Thank you.